Hello, welcome to this video. Today we're going to look at this problem. So, this is the problem. We have the limit as n approaches infinity of 1 over n squared times the sum as k goes from 0 to n of the square root of n squared minus k squared. And we need to calculate that. So, at first, the first thing that I thought about when approaching this problem is that this looks a little bit familiar to this function y is equal to the square root of 1 minus x squared, which when plotted on the xy graph just looks like the top of the unit circle. So the radius here is 1, so all these lengths are 1, and it's just a half circle on top of the x-axis, half of the unit circle. And pretty much you can see where that comes. Where that comes from, we have the square root, and then we have something minus some parameter k or x squared. And because this is n squared, if we actually divide this by n, we can make it so we divide this inside expression here by n, which will get us this form of y is equal to the square root of 1 minus blank squared. So let's see, and we will divide it by n also by using one of these 1 over n squares. So we'll have left 1 over n times the sum as k goes from 0 to n of this square root of n squared minus k squared, that divided by n. So what we have here is the limit as n approaches infinity of 1 over n times the sum as k goes from 0 to n of the square root of n squared minus k squared divided by n. And now we can put this n inside of the square root such that we get that on the inside we have n squared minus k squared divided by n squared, giving us the square root of 1 minus k over n whole thing squared, which again is the form we were looking for, square root of 1 minus blank squared. So that's what we get. So let's just replace the inside of the sum with this expression. So we have the square root of 1 minus k divided by n squared. Alright, now that we have this, what I say is look maybe how it looks geometrically. Maybe we'll look again on the y plane. If this k over n was x, and the square root of 1 minus k over n, that thing squared, was y. So, if we plot it like this, so this is x, k over n, and this is y, which is the inside of the sum, k going from 0 to n, meaning that our x variable, which is k over n, and the sum goes like this. It's 0 over n, then 1 over n, then 2 over n, all the way until n over n, which is 1. Meaning that we sum all the fractions, which are something divided by n, from 0 to n, which are fractions from 0 to 1. And let's look at the actual value. Well, like we said, again, x will be going from 0 to 1 with these fractions 0 over n, 1 over n, 2 over n, and so on until n over n. and the actual value when we input it is what we get in our y, which is the square root of 1 minus x squared, which, like we saw earlier, is the plot of half of the unit circle on top of the x-axis, the top half of the unit circle. Meaning that what we are doing is looking at the unit circle and grabbing each value of it from 0 all the way on to 1 with all these fractions of something divided by n in between. And what we get is that we're looking at these values. So this is the value k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, and so on. So k is n, and k over n, which is x, is 1, and our value at y is 0. And that's essentially the top half of the unit circle hitting the x-axis. So, and now what we're doing here is looking at these values, or these lengths of these lines. And now, and we're summing the lengths of all these lines. And then what we're doing is dividing this by n, since we still have a times 1 divided by n, and we're taking the limit as n approaches infinity. And let's see. Well, we have n plus 1 points plotted here, and n plus 1 values we are summing, since k goes from 0 to n. Meaning that if we look at the gaps, we have n gaps between those points geometrically. And those are also all equal distances along the x-axis. So I'm saying that this is equal to this, is equal to this, and so on. And all these lengths add up to 1, the radius of the unit circle. And because there are n of them, it means that each one of these lengths is 1 over n. So this is 1 over n, then this is 1 over n, then this is 1 over n, and so on. And this is actually the exact 1 over n we have inside the limit. So what you can say is we're taking each one of these top standing values and multiplying it by these short distances. So what I'm saying is it's this times this plus this times this plus this times this, and all the way down. This ensures we have each number inside the sum accounted for multiplied by 1 over n. Then we sum it up, and that's what we get. And what we want to find is, as n grows larger and larger, what this sum approaches. Well, as now this can look oddly familiar to a video in the past about the area under a function that's above the x-axis, which we showed as the integral of that function. And what we said is we're taking stripes and essentially doing lines with their x values being the same distance away from each other, and cutting lines along, and then we're letting the amount of those lines approach infinity, so each 2 consecutive lines approach closer and closer to making a rectangle with the top of the function, the bottom of the x-axis. And this is exactly what happens here. n approaches infinity, then we have more and more lines that each two consecutives together with this part and this part make approach to make a rectangle. And the area of a rectangle is base times height. So the area of each of those rectangles is the value, the length of the line times this bit next to it. So this times this plus this times this plus this times this and so on will give you the area as n approaches infinity, which is the exact value we calculated for this limit. We know that is the exact value of this limit too. So summing the areas of all these rectangles, giving us the full area of this quarter circle, because remember this is half of the original half circle we had, is the sum of the areas of all these rectangles, which we just showed is the value of this limit. So this limit is equal to the area of a quarter of a unit circle. So let's mark it like this. Now the area of a regular circle is pi r squared. The radius of the unit circle is 1. That's the definition of it. So the area of the unit circle is pi. And meaning that the area of a quarter of a unit circle is just that, a quarter of pi. Meaning that this gives us pi over 4. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems like this in the future. And finally, that's it.